Okay, hello everyone. We're going to introduce numerical methods, and in numerical methods, we shall start with the graphical approach of locating the roots of given equation. So, location of roots is what we're going to look at here. And what are roots? If they ask you what is a root, given any function, let's say f of x equals to 0. F of x equals to 0. That's the function of, it's a function of x. They can ask you to solve this function. You're simply going to look for the value of x that if you substitute in that function, it gives you a 0. If you can recall your O-level quadratic equations, that's what we're doing. We're solving quadratic equations by simply finding the values of x that if you substitute the function becomes 0. In that case, we shall say we've solved the equation. In this case, we're going to look at how we can locate the position of that root, position of the value of x that if you substitute in the function, it becomes 0. There are many approaches. There are two approaches. It's one we call sign change approach, and the graphical approach. Let's look at the general objective of this topic. We're saying you should be able to tabulate values, to use tabulated values to draw a graph. You've done this in O-level already, where you solve the quadratic equations using graphical approach. You just got values, a function, got values of x, they give you the domain, then you plotted the functions and looked for the point at which the function crosses the x-axis. In that case, you're solving that equation by graphical approach. That's one of them. Then the other one is to locate the position of the root by noting this change in sign. We're going to look at that in details later on. Now, what are the specific objectives? One of them, you should know how to sketch graphs of a function. I think you did that in O-level. You sketched very many functions before. Then estimate the root of the equation f of x equals to 0 using graphical approach. Yes, I can draw a graph for a function. Let's say I have it like this. When the function crosses x-axis at that point, we note that the root of this function is somewhere there. It lies almost at that point. So we're going to look at those details also. Then show that the roots or the root or exists in a given interval. Yes, my function crosses the x-axis at this point. Maybe we have 1 here, we have 2 here. I may not be interested in the root itself, but the interval in which lies. In this case, my root of the function, this function f of x, lies in the interval 1 and 2. So that's the other thing that I can ask you that we're going to look at in this topic. Then also estimate the root of a function f of x using sign change. We shall look at that in detail later on. Show that the roots exist in a given interval using sign change. We shall also look at that in details. Now, topic breakdown from the objectives above, we have only 2 concepts we're going to learn here. One of them is location of roots by graphical method, plotting. Another one is location of roots by sign change method. There we shall also look at it, sometimes called analytical method. We're going to look at that at a later time. So let's look at the very first one, location of roots by graphical method. We're saying this involves plotting the equation y equals f of x, where f of x of course will be 0 for given values of x, and noting the intervals or the interval along the x-axis within which the root of the equation lies. You simply plot the function, they give you the domain, then look at which interval will it cross the x-axis. That tells us that the root lies between some. If the function doesn't cross the x-axis, means that the function has no root in that interval. So it is also broken down into 2. We have a single graph method where you plot the whole function given. If they give you a function y equals f of x, you get the values of y by substituting the x values in the function. Then you plot a graph of y against x. Then you note the values along the x-axis between which the curve you plotted crosses the x-axis. and that will give you the interval within which the root of the equation lies. Let's have a simple illustration. Look at this graph here. You plotted your f of x. Let's say you have a function f of x. You plot it, and you notice that this curve you've obtained crosses the x-axis twice. It is crossing the interval a and b, and also crossing the interval c and d. This confirms that the function you plotted has two roots, has two real roots in the interval a and d. It has two values. There are two values for this function between a and d that if you substitute this function, it becomes 0. That's what it tells us. It means that at this point, y is 0, and at this point, y is 0. And therefore, the values of x at these points are what we call the roots of the function. On the left hand, on your right, you can see that the function you plotted does not cross the x-axis at any point between a and d. So that means that this function has no real roots. So how do we conclude after obtaining such curves? You will say the curve cuts the x-axis twice between a and b. What does it imply, therefore? That implies that f of x has two real roots in the interval CD. You can see that it's crossing the x-axis in that interval, and AB. That's how we conclude. Because the function crosses the x-axis twice, therefore it has two roots. This one does not cut the x-axis at any point in the interval AD. So that means that the function you plotted has no real roots in that interval. That means that you can't get any value between a and d that you can substitute in this function and it becomes 0. So it has no roots in that interval. Now, what if the function has more than two roots? How will the curve look like? We shall have something like this. And something like that. Now, you notice that this function is crossing the x-axis 3 times. If it is crossing 3 times, that means that the function f of x has 3 roots. So that therefore means that the number of times a given curve crosses the x-axis shows the number of roots a given function has. If it crosses once, it has 1 root. If it crosses twice, it has 2 roots. If it crosses thrice, it has 3 roots, and so on and so forth. If it doesn't cross at all, it means it has no root at all in that interval. That's what you should note from this. What if you're using 2 graphs? How does a 2 graphs plot work? So you'll be given a single function, or you may be given 2 functions. If they give you a single function and they want you to use 2 graphs, then you must know how to split. So if they give you 1 function, you split it up into 2 functions, y1 and y2. You do it in such a way that one of the functions is a linear function and another is a curve. We do this for convenience because plotting a line, a straight line is easy. So while splitting, you should not create 2 curves to give you hard work. So what you do, just split it in such a way that one of the functions is a straight line and another one is a curve. How do you know that a given function is a straight line and another one is not? So all functions which have variables, and those variables, the power of the variable is not 1. Those functions will always be curves. If you have a function which has a variable whose power is not 1, that function will be a curve. Look at this. If you have, let's say, x squared plus maybe 3, maybe x cubed plus maybe 4, maybe x power half plus something or 10. So in any function where you see the power of a variable is not 1, that function will always give rise to a curve. Even x power negative 1 plus maybe 2. This is also a curve because the power of x is not 1. This is not 1, this is not 1, this is not 1. So that will give you a curve. Also, trig ratios, trigonometric ratios like sine theta, cosine theta, or x tangent, x, cosec, sec, all those ones will give you curves. All trig ratios will be curves. So while splitting, make sure those trig ratios remain along one side because it will give you a curve, and the others, the linear function on the other side. Also, logarithms. Logarithms will also give you curves. So you split, when you're splitting, leave them on one side. Those are curves. So while splitting, split them in such a way that one of the functions is a curve and another one is a straight line. All functions will form x plus 1, x plus 2x plus 3. All these are straight line functions. Functions with variables which have a power of 1 will give rise to straight lines. We do it in that case, do it like that because straight lines are easy to plot. So you should not create two functions which are both curves. They will take a lot of time. But if you have no option, then you have to do it. So the values of y1 and y2 are obtained and tabulated. Then you plot y1 and y2 against x on the same axis. Then you note the point of intersection of the two lines. Notice that in the first case, we're interested in the point at which the curve crosses the x-axis. In this case, our interest is in the point where the two lines intersect. Let's have a simple question here. Look at this curve on your left-hand side. You notice that we plotted y1 and y2, and they're intersecting twice in the interval A and D. They're intersecting 2 times. So this confirms that the original function you split has 2 real roots. One is between A and B, and another one is between C and D. So how do you conclude? You say the curve and the line intersect twice between A and B, and between C and D. So that means that therefore the function f of x has 2 real roots. And then on this other side, the right hand side, is that we plotted the function this and that, but they're not intersecting at any point. That confirms that the function is split has no real roots. Now also, if the function has more than 2 roots, then the 2 lines will intersect more than twice. 3 times 3. So you plot something like this. Maybe you have that, you have this. You notice that this one, they're intersecting at this point, intersecting here, and intersecting here. That confirms that the function split has 3 real roots. So in this case, the number of times the lines intersect gives you the number of roots that a given function has. I think that is clear. Let's now have a simple example. The saying show that the position, show that the positive real root of the function, this function, lies between 0 and 1. Now, our interval, they want us to study the behavior of this function between 0 and 1. So we restrict ourselves to only this interval. Because this function, if it is a quadratic function, that means that there are 2 possible values of x that will satisfy this function. But now, they're telling us to study the behavior of this function between 0 and 1. We restrict ourselves to that. Because if you go beyond the interval given, you may go to the region where the other root also lies. So here, when they say between 0 and 1, study the behavior of this function only between 0 and 1. Don't go beyond that. If you go beyond that, then your answer will be wrong. So we're going to solve this using the 2 approaches and see if it will give us the same result. So what we do, we split up the domain given. The domain given is 0 to 1. So I use a convenience scalar to be 0, 0.1 up to 1. Notice that in my table, I only have values between 0 and 1. Then I generate the corresponding y values. You can do this by computing. You can save time. Instead of typing the function all the time, you can feed the function the calculator at once. You simply say you have 2x squared plus 3x minus 3. It is 2 alpha x. You have something like that. After putting the calculator, then squared, you square it, you have something like this. And then plus 3x, 3 alpha x. When you want x, x is in purple, so you have to use the alpha. And then minus 3. Then you say calculate. You'll have the calculator ask you for the value of x you want to input. You have something like that, x question mark. So my first x is 0, I put there 0 equals 2, it gives me negative 3. My next value of x is 0.1, so 0.1, I go again to calculate. It asks for the value of x, I put there 0.1 equals 2, it gives me the value of x, like that. So you keep on generating them like that. So after that, I have my values of x and values of y. The next thing is plotting them. Remember, I'm using single graph method. So I'll have something like this. This is my graph. I've restricted myself in the interval given, to the interval given, that is 0 and 1. You notice that my curve starts at exactly 0 and ends at exactly 1. Doesn't go beyond that. That's one thing you must note. Then also, while joining this curve, join it using a free hand. Don't use a ruler to join the points. Join using a free hand. If you use a free hand, you end up with a smooth curve like this. If you use a ruler, then your answer will be wrong. Then also have as many points as possible, because curve changes almost at every point. So the more the points, the more accurate your curve will be. If you use very few points, it will be very inaccurate. Also use a very big enough graph by using a small scale, so that if they ask you to read the initial approximation of the root, it will be very accurate. So that's what you do. You plot a graph like this. There are some elementaries you learned in O level, labeling the axis. You have the x-axis, the y-axis. You should also label your curve. Your curve is y equals 2x squared plus 3x minus 3. So when you have something like this, it's okay. So how do you conclude? They said you show that the root of this function exists in the interval 0, 1. And we notice that the curve is crossing the x-axis in the interval given. So that confirms that the root exists. So here we shall say the curve cuts the x-axis once between 0 and 1. There is therefore a positive real root of the equation in the interval 0, 1. The interval must be here. So that is it. Did they ask for any other thing? They said, yeah, lies between 0, 1, and that's what we've done. Our interval is, our root lies between them. So here I've stated the approximate root, but you may not state it. So what if the root never existed in the interval? How would the graph look like? What if this function has no root in that interval? How would the graph look like? If you draw your graph, we have 0 here, we have 1 here, and our curve is like this. It is not crossing the x-axis between the given interval. So therefore, that confirms that the function we're plotting has no root in that interval. It can also be like this. You can also plot and it is like that. It is not crossing the x-axis between 0 and 1. That confirms that the function has no root. Yeah, so what you should note here, when drawing the curve, use a free hand so that you end up with a smooth curve. Another one, restrict yourself to the interval given. Don't go beyond the interval. Then the other one is get the points, draw a big graph by using a small scale. Alternatively, if you're using a 2 graphs plot, what will we have? So you have to split this. We said you split it in such a way that you have a linear function and a nonlinear function. So I simply take the linear part the other side. I have 2x squared plus 3x minus 3 equals to 0. I take the linear part on the other side, and I'll end up with a linear function and a nonlinear function. Then I also split my domain. I'll have the x values. I have my first function here and another function there. So I keep substituting the x values in these functions and I'll end up with this table. Afterwards, I plot. When I plot, I'll end up with that and that curve, the curve and the straight line. So you also notice that I've restricted myself again in the same domain given 0 and 1. The straight line is here. You can have 2 points for straight line. You don't need very many points for a straight line. But for a curve, you need very many points. The more the points you use, the more accurate your graph will be. So you also have to label. This is a straight line. I label it y2 equals this and y1 equals that. Then you also note the root. They said show that the root exists. Give us evidence that the root exists. Don't just draw and leave it there. So you draw a dotted line, use a dotted arrow, and write somewhere the root is somewhere here. The root exists between 0 and 1. So your conclusion will be the two lines intersect once between 0 and 1. The equation has a real root in the interval given. Next example, they're saying use a suitable graph. Using a suitable graph, show that the equation this has a real root in the interval 0.1 and 0.8. Hence, state the approximate root. So in this question, they want you to state the root. So we have this. Here I'm going to use a single graph method. See, they have not restricted me to use any method, but since they have given me one function, there are no equal signs, I'll use a single graph method. So I have this. Still, you can feed the whole of that function in a calculator by simply, you have exponent. So I go to shift exponent, 2x, I open brackets, 2 alpha x. When I want x, I'll have something like this, 2 alpha x. Then I close, sine x, sine alpha x, I'll have something like that. The whole function is there, minus 1. I say calculate, if you ask me for the value of x to put. So I put 0.1, I say equals to give me this. This is my first one, negative 0.878. I can use to leave this. Again, calculate 0.2. What do I get? It gives me that. Again, calculate. So that's how you save time. 0.3 equals to. We have that. Then the other thing you have to do here is when you see a trig function, now like this, you have sine x. That means that your calculator should be in radian mode. It should be in rads mode. You do it in degree mode, you're going to get wrong values because these are small angles. These are small values. They're not. These cannot be in degrees. So you have to change your calculator to radian mode before you input the values. Radian mode, you go to mode. There is mode here. You press it. If you have an original calculator, it will be something like this. Then you choose 2. When you choose 2, you have that small r. It can't be seen here very well, but you see a small r. That shows that the calculator is in radian mode. If you leave it in degree mode, all the answers you get will be wrong. And you end up with a wrong graph, and you lose all the marks. So my graph will be like this. Still, you see that the smooth curve, I'm restricting myself to the interval that is 0.1 to 0.8. And I'm joining my points using a free hand, a smooth curve, not a ruler. Then the other thing is I've labeled my curve. I have a title for my graph. I have, my graph is big enough to cover the biggest percentage of the graph paper. So this is a perfect graph. When you draw, you don't use a convenient scale or an appropriate scale, you end up with clustered points. Points will be together and you fail even to draw a line. So make sure you spread. And your x-axis at this point, I start from my minimum value of the interval. They said x equals to 0.1 and 0.8. So my starting point here on the x-axis will be 0.1. You have to take note of that. If you look at the previous graph also, they said 0 and 1. My x-axis starts at 0. This one, they said 0 and 1, I started from 0. Here they're saying 0.1 and 0.8, I started from 0.1. So the minimum value of the domain given gives you the starting value of the x-axis. Here we're interested in the point at which the curve crosses the x-axis. So that means that the y-axis should start from 0. Since we're looking for the x-intercept, the y-axis should always start from 0 when you're using a single graph method, because our point of interest is the point at which the curve crosses the x-axis. So it crosses it when x is 0 and when y is 0. So therefore, y should start from 0. That's what you should also take note of. So how do you conclude here? We say since the equation, since the curve crosses the x-axis between x equals to 0, 0.1 and 0.8, since it crosses it once, the equation given has one real root in that interval. Example 3. Example 3, they are saying show graphically that the equation this has a real root in the interval 0, 1. So still, like we've been doing this, in this case, you're going to use a two-graphs approach. Why? Because they have split the equation for you already. We have one part on this side and another on the other side. You can see x, exponent x, and x plus 1. So we shall have one of our functions as x, exponent x, and another one, x plus 1. Notice that one of them is a curve and another one is a straight line. This exponent here, this lies in the category of logarithms. This is natural log. Then this one is a straight line since the power of x is 1. So still I have my y1 as this, my y2 as that. Then I split my domain like I've been doing. They are saying between 0 and 1. So I restrict myself to that interval 0 and 1. I split it up using a convenient scale, that is 0.1. So I keep substituting. Still, how do I get x, exponent x on my calculator? X is in purple, so I use alpha, alpha, x. I'll have something like this. Exponent, that is shift, exponent, I have that. Then x, x, alpha, x. You have that on your calculator. Then you simply say calculate. What's my first value of x? 0. Put there 0 equals to, gives me 0. Calculate again, put there 0.1. 0.1 equals to, it gives me that. Then you calculate again, 0.2 equals to, I have that. So that's how you generate those values. Then also x plus 1, after that you can remove that function and put another one, x plus 1. Here I don't have a trig functions. So therefore I'm free to operate my calculator in degree mode or in radian mode. That doesn't affect the result. But when you see a trig function anywhere, the first thing, that's the failing point for most of the students. They forget to change the calculator to radians when they have trig function, and they fail it. They fail the question. So the graph, my graph will be like this. I've plotted the two functions. Notice that they are ending at exactly 1 and starting at 0. I have my straight line. Straight lines, even if you have 2 points, remember your O-level mathematics, 2 points are just enough for you to have a straight line. Then a curve, we need as many points as possible to have an accurate curve. Imagine if you did not have all these points in between and you had only this second point and the other one. That means that your line will come along here. To come along this, and the intersection will be at a different point altogether. So the more the points, the more accurate the curve is. Join the curve, the points of the curve, using a free hand. A straight line, you can draw it using a ruler. Make sure you restrict your lines within the interval given. You also have to take note. They say they want you to show that the root exists. You've shown them here that the root is somewhere here. You've shown them. Remember, two-graphs method, we are interested in the point of intersection of the two lines. So even if none of them crosses the x-axis, that's not our problem. Our problem is the point of intersection. The x-axis should always start from the minimum value of the interval. For two-graph method, you're free to start your y-axis from any point of convenience. I think that is noted. Single graph method, x-axis, the y-axis, the values on the y-axis should start from 0. Two graphs approach, you're free to start from any point on the y-axis, because we're not interested in the point at which the curve crosses the x-axis, but we're interested in the point of intersection of the two lines. They can intersect at any point. Example next, they're saying on the same axis, draw a graph of y equals this and y equals that. This is clearly a two graphs approach. They're saying on the same axis, draw graphs. So how do you know which method to use? Two graphs, single graph. The question will always give you a hint on which approach to use. If they say on the same axis, draw graphs, that is already telling that you should use a two graphs approach. Or if they split the function already for you, like in the previous example, that is already two graphs approach. In example, in this example of example 2, they gave you a single function which they are not even split. So in this case, you're supposed to use a single graph method. Okay, so here we have that. You label your graphs. You have this. You have labeled that. I've noted the points. How do I conclude? Since the two lines intersect once in the interval given, then the equation that has a root in the interval given. Example next, they're saying on the same axis, draw graphs. Draw graphs. This is also two graphs method. Draw graphs of, I didn't include it. Okay. Draw graphs of that to show that the root of the equation is draw graphs of this to show that the roots of the equation lies in that interval. This is a two graphs method. So you still generate our functions, split the domain. We want between 1.0 and 1.2. So I can use a scale of 1.1, 1.0, 1.10, 1.11, up to 1.20. Then I generate the corresponding values of y equals tan x and y equals to x. By using the calculator, I can simply say tan alpha x, then calculate. Then I keep inputting the values, something like that. Keep inputting the values. I generate the values of y equals tan x and y equals 2x. I plot them on the same axis. They'll end up with such a curve. So we shall say this is a graph of that. I label this. This is y equals this and y equals that. I take note, since I wanted to make sure that the root exists, I show them that the root is here. So you should also write somewhere here, root. Show them that the root is actually there. Then I've used, this is a curve, I've used a smooth, a freehand. This is a straight line, I've used a ruler. So I've restricted myself the domain that is 0 and 1.20. You notice that my x-axis, the values on the x-axis are starting from the minimum value of the interval given. That's 1.10 to 1.20. Then the y-axis, since I'm not interested in the point at which it crosses the x-axis, I'm starting from 1.9. I need to have a convenient scale. I should not start from 0 again, because I'm not interested in the x-intercept. I'm interested in the point at which the two intersect. Okay, so that is it. How do we conclude? We shall simply say, since the two lines intersect once in that interval, the equation this has a root in that interval. So what we do here, summary, that marks the end of graphical approach. So the key points that we need to note in here, we have to note that For a given question, you can use a single graph approach or two graph approach, depending on how the question has been formulated. I think you can refer to those examples to find out which one requires two graphs method, which one requires a single graph method. If they give a function with equal signs in it, with one function, if they have speech already for you, then there you have to use two graph method. Or sometimes you say by drawing suitable graphs on the same axis that show that you want you to use two graph method. Then for single graph approach, look out for the point at which the curve crosses the x-axis, that's the x-intercept. And you have to note that the y-axis should therefore start from 0. For two graphs, look out for points of intersection of the lines, the curve and the straight line in most cases. Look out for that point of intersection. Then trig ratios, if you have trig ratio, that is sine, cosine, tangent, cotangent, secant, cosecant, and logarithm functions. And functions with variables with powers are not 1, will always be curves. That's what you should know. They will always be curves. So while speaking, you have to take note of that. Then always change your calculator to rad mode. For trig ratios, trig functions, when you see a trig function or trig ratio in any function, then change your calculator to rad mode. Join points of the curve with a free hand, but not a ruler. This is how we join points. If I have a point here, a point here, a point here, you join it with a free hand. That's what we're talking about. Don't have a point here, a point there, a point here, then you use a ruler like this and a ruler like that. That's not a curve. This is not a smooth curve. This is a smooth curve. That's what you should know. Then restrict the lines in the interval given. If I'm studying the interval 0, 1, and I have, let's say, that point like that, I stop at exactly 1. If you take it beyond like that, you can't see it. If I take it beyond, this is 0, this is 1. I take it beyond like that, this is not to be a wrong curve. If I'm investigating the behavior of this function f of x in the interval 0, 1. Then the other one is always label the lines. That will, if you don't do it, it will lead to lots of marks. Use a convenient and appropriate scale to come up with a clear and big enough graph. If you use a very big scale, you end up with a very funny scale, a funny graph. So choose a convenient scale. You can use some of the knowledge you acquire, you learned, the techniques you use in O-level physics while drawing graphs. Then also mark the points where the approximate root lies. Yes, like I've been marking here. I want to show that the root exists. So show them that the root is somewhere there. Show them that the root exists. And write there the word root to show them that you found what they asked you to find. Then start the x-axis with the minimum value of the interval. Yes. If they say interval 0, 1, your x-axis should start from 0. If they say interval 1.2 to 1.3, your x-axis should start from 1.2. That is for positive values. If they are negative, of course, the x-axis should start from the maximum value. Look at this case. In this case, question they were saying between -1 and 0. So my x-axis starts from 0 towards the negative. So in this case, 0 is the maximum. So for negative values, x-axis should start from the maximum value towards the negative values. If you have positive values, my x-axis should start from the minimum value towards the positive. That's what that point means, and many others. So this question is popular. If you have a question bank, you can look out for them. It's a very popular question, but again, easily failed if you don't take note of those key points. These points here, make sure you take note of them. Any error made in this will make you fail your question. And it is always linked up to other topics. It is linked to like trapezium rule. It is linked to linear interpolation. It is linked to neutron Rankson method. So, and this is always the first part. So if you fail from here, then all the other parts will be wrong. And how do you fail? By not following these key points. By not following these key points. If you join just not drawing a smooth curve, joining them using a ruler will make you fail also. So in other methods, they'll ask you to read the initial approximation from here and substitute somewhere else. So if this is wrong, then they will say you can't get a wrong value from a correct, you can't get a correct value from a wrong graph. So everything will be considered wrong. So you have to just be careful and follow everything to the dot. These marks will always be there. Therefore, if you keep practicing, we've learned it quite early so that you have enough time to practice. So exercises here. You try out these numbers, try them out, scan your working, and send your work to this. Thanks for watching. You go to gmailmath.com. That's where you find these ones for some of you missed. Then afterwards, you email your work, your answers to admin@gmailmath.com. I'll go through it and give you the feedback. Yeah, thanks for watching. We'll link up in the next lesson.